Students and friends, welcome to my new video, which is a sequel of my previous video upload on elastic properties of solids and liquids. This time around, I'll be discussing problems, of course, with solutions involving Hooke's law. So, just relax, watch and learn. So, what is this law called Hooke's law? Well, this law simply states that in elastic deformations, stress or force per unit area is proportional to strain, the fractional deformation. The proportionality constant is called the elastic modulus. And this elastic modulus can be determined by just dividing the stress over the strain. Incidentally, this was discussed in my previous video tutorial. Alright? Now, there are limits of Hooke's law. There is such thing as the proportional limit. It is the maximum stress for which stress and strain are proportional. Beyond the proportional limit, Hooke's law is not valid. Alright? The so-called elastic limit is the stress beyond which irreversible deformation occurs. And the third equally important concept is the so-called breaking stress or the ultimate strength. It is the stress at which the material breaks. To clearly understand what I just described earlier, let's look at this diagram, which is a typical stress-strain diagram for a ductile metal which is subjected to tension. Along the x-axis, all right, we graph the amount of strain in percentage. Along the y, we have the corresponding tensile stress. All right, so there are three regions that are worth mentioning here. From point O, right, this is point O. Point O means zero strain and zero stress. So from point O to point A, we say that the Hooke's law is obeyed. And if you notice, the graph line is a straight graph line sloping upward to the right. All right? So during this particular moment when the strain increases linearly for a corresponding amount of stress, okay, the two quantities, stress and strain, are directly proportional, and that's exactly what the Hooke's law is telling us. So we call this point A as the proportional limit. All right, so the graph line, the straight graph line colored green, is what we call the elastic behavior, or shows the elastic behavior of this ductile metal that is under tensile stress. Now, from point A to point B, Hooke's law is no longer obeyed. All right. It is because this graph line or curve doesn't anymore suggest that the stress and the strain are proportional. The fact that this is no longer straight, the graph line is no longer straight. So we say that Hooke's law is no longer followed or obeyed. And point B, all right, point B here is referred to as the elastic limit, all right, or we call it the yield point. That is point B, right? Now, what's significant about this elastic limit or yield point? Well, for as long as the amount of stress, okay, is not exceeded and the amount of strain is what is represented by point B, when the load is temporarily removed, well, the body will be able to return to its original shape or length as if nothing happens, right? In other words, this graph line from point O to point B is irreversible. Is reversible. All right. Now, what happens when the amount of tensile stress is exceeded beyond that elastic limit? All right. So, what happens is the behavior of the material definitely does not behave as if Hooke's law is still followed. All right. From point O to point B, we say that the material still shows an elastic behavior. All right. But beyond that, all right, beyond that elastic limit or yield point, the material doesn't show an elastic behavior anymore, but it's possible that it is behaving like a plastic, all right, material. We call it the plastic behavior, okay, represented here by the graph line colored red. So, if the amount of tensile stress is at point C, right, with the corresponding strain, and if the load is removed temporarily, the body will not be able to go back to its original size or shape. We say that it is already permanently deformed. All right? And that value of the strain here at this point is what we call the permanent set strain. All right? So, for a small amount of tensile stress added, all right, beyond the what we call elastic limit, all right, the amount of percentage of strain is large, as shown by this longer curve sloping upward to the right, but greater amount of strain is obtained, all right, until the graph reaches a point which is referred to as the fracture point or the breaking point of the material. All right, fracture in the sense that uh, beyond that point, the body is already broken. All right, or fractured. Hence the word fracture point. Now, obviously, the kind of ductile metal used here is one that has exhibited a plastic behavior, all right? A plastic behavior, not just an elastic behavior, but also what we call a plastic behavior, all right? So, if you're going to compare two metals such as iron and steel, all right? In terms of elastic modulus, or the Young's elastic modulus for these two metals, their elastic or Young's elastic moduli are almost the same. Okay? For iron, it is 21 raised to the 10 power Pascal, while for steel, it is just a little lower, 20 raised to the 10 power Pascal. Okay? But looking at their breaking stress here, the breaking stress for iron has a magnitude of 3.0 raised to the 8 power Pascal, while the breaking stress for steel ranges from 5 to 20 times 10 to the 8 Pascal. So, while these two metals are considered stiff, very stiff, as compared to other common materials, right? In terms of strength, all right, or their ability to uh, withstand what we call tensile stress until they break, it looks like that the steel is, we say, is stronger compared to iron. All right, our first question is a conceptual question. While parking your car, you accidentally back into a steel post. You pull forward until the car no longer touches the post and then get out to inspect the damage. What does your rear bumper look like if the strain in the impact was, situation letter A, less than at the proportional limit? Situation letter B, greater than at the proportional limit but less than at the yield point. Situation letter C, greater than at the yield point but less than at the fracture point. And situation letter D, greater than at the fracture point. So here are the descriptions, okay, for you to choose from for each of these four situations, all right? Which among A, B, and C, all right, will match each of these situation? Option letter A, the bumper will have sprung back to its original shape, although the paint may be scratched. Option letter B, the bumper will have a permanent dent or deformation. Option letter C, the bumper will be torn or broken. So, what do you think are the answers to each of these four situations? Right? The correct answers are, all right, for situation A and situation B, all right, this is how we describe the bumper. It is option letter A. The bumper will have sprung back to its original shape, all right, although the paint may be scratched. So in other words, the material, all right, the metallic material that makes up the bumper has just been, subjected to a relatively small amount of stress, right? And the elastic behavior of the material is evident. That's why our answer is letter A, because according to the situation A, uh, the bumper looked like, the strain in the impact was less than at the proportional limit, all right? And for situation B, greater than at the proportional limit, but less than at the yield point. So both situations A and B, all right, suggest that the elastic limit has not been exceeded. And the sign of damage, all right, is that described in option letter A. Now, for situation B, or C, I should say, for situation C, the correct answer is option letter B. The bumper will have a permanent dent or deformation because, as described in letter C, all right, the strain in the impact was greater than at the yield point, but less than at the fracture point. So we expect that uh, the bumper will have a permanent dent or deformation, but it is not broken. Finally, the answer to situation D is, of course, option letter C. In situation letter D, we say that the strain in the impact is greater than that at the fracture point, right? So it's obviously suggesting that the bumper is already torn or broken. All right, so question number 2 is a quantitative problem. In a material testing laboratory, a metal wire made from a new alloy is found to break when a tensile force of 90.8 newtons is applied perpendicular to each end. If the diameter of the wire is 1.84 millimeters, what is the breaking stress of the alloy? So our solution to this question is just to determine the amount of breaking stress, whose formula is just equal to the amount of force, right? The amount of force, tensile force that is, divided by the cross-sectional area of the metal wire. Take note that the tensile force in this situation, as well as in this formula, the tensile force is perpendicular, okay, to the surface area of the cross-sectional area of the metal wire. All right. So, since tensile force is given and the diameter of the wire is also given, we just plug in those given quantities to this formula. That is 90.8 newtons is the tensile force. Okay, and that will be divided by pi r squared. All right, the formula for the cross-sectional area of the metal wire. Since what's given in the problem is the diameter 1.84 millimeters, there is a need for us to divide that by 2 because we are only getting the radius, and that the radius is just half the diameter, and of course express radius in meter. All right, so when 1.84 millimeter is divided by 2 and then converted to meter, that is equal to 9.20. All right, the three significant figures raised to the negative fourth power. All right, and that will still be squared before we do our division. So when you do your math, we will get this amount of the breaking stress of this alloy equal to 3.42 times 10 to the 7 power Pascal or Newton per meter squared. Our last question, question number 3. A steel cable with cross-sectional area 3.00 centimeters squared has an elastic limit of 2.40 times 10 to the 8 Pascal. Find the maximum upward acceleration that can be given a 1,200 kilogram elevator supported by the cable if the stress is not to exceed one-third of the elastic limit. So our solution, we first determine the force of the steel cable given the stress and the cross-sectional area. So, uh, 2.40 times 10 to the 8 Pascal, which is labeled here as the elastic limit, will be the amount of stress that we will consider. Alright? Then if that is multiplied by the cross-sectional area in meters squared, okay, we will get the tension force. Right? But the area is already converted to meters squared. So that is 3.00 raised to the negative 4 meters squared. Doing our math, we will get the value for the force, all right, equal to 7.2 raised to the 4th power Newton. And we can now calculate for the acceleration, all right, using Newton's second law, A equals F net divided by the mass. Since we want an acceleration that is directed upward, it simply means that the upward tension exerted by the cable, all right, must be greater than the gravitational pull of gravity on the elevator. So F net therefore has to be T minus mg, all right, so that the F net will be upward. And then that will be divided by the mass. When we substitute, all right, the tension that we are using here is equivalent to one-third of the elastic limit, and one-third of 7.2 raised to the 4th power Newton is 2.4 raised to the 4th power Newton. All right. Then we subtract the weight of the elevator, that is the mass. All right, 1,200 kilogram multiplied by g, 9.8 meter per second squared. All right. And then after getting the F net, we will divide it by the mass, 1,200 kilogram. And again, doing our math, we will get the value for the acceleration equal to 8.5 times 10 to the negative 3 meter per second squared. All right, and this is relatively a low value for the acceleration. Okay, so that's it. Thank you very much for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.